So, yeah, my name is Felice. I'm a particle physics in the physicist in the experimental physics department at CERN. So, I will give you also, since this is the first talk on high energy physics, there will be I will also give you an introduction on why we need such large scale training softwares for infrastructure for training neural networks on a distributed and high performance computing system. So what we are doing at CERN is basically trying to reproduce in small scale the Big Bang, which means transforming energy into particles, trying to excite new fields which may produce new particles. So for doing that, we are making bunches of protons containing 1 million protons each, colliding every 25 billionth of a second. They produce new particles that did not exist before the collisions, and these new particles fly through the detector. Now, what you see here is the filtering of these 40 million events, pictures that we have taken with our detector, because we cannot store basically 1 exabyte every single second. So basically we do that with a level 1 filtering, which is based on electronics, and then we have an high level trigger, which is based on a traditional PC farm. It's usually, we are talking about 30,000 CPU cores that run software, C++ based software, and then these can filter basically interesting events, one interesting event in 1,000. Then these products coming out of the high level trigger farms, which are sitting in the collision, up the collision points, are going to the CERN data center, where we reconstruct these data, and basically then we send all these data all around the world using the worldwide LHC computing grid. So basically all these data is replicated and can be analyzed by physicists basically all around the world, sitting close to these tier 0. It's basically a tree-like structures. Now, the kind of camera that we use to take these pictures, it looks like this. It's not one-to-one scale. It's basically 15 meters times 15 meters and 25 meters in depth. It weighs about 14,000 tons. It's about twice the Eiffel Tower in Paris. But unlike the Eiffel Tower in Paris, you have 6,000 sensors per square centimeter. So basically, collisions happen in the center, and new particles created in the collisions fly through the detector, leaving tracing signals, energy deposits that we study. We basically try to connect the dots with all these signals and try to assign each single dot energy deposit to the particle which has produced it, and trying to understand the basic properties of all the, for example, in this case, tracks, so trajectories of particles. So we want to understand what is the momentum of the particle which has flown through the tracker, the energy by connecting this track with the calorimeter. So why we are doing this? So in 2012, you might have heard that we completed what we call standard model of particle physics by adding this new particle which we have in the center, the H, the Higgs boson. But the problem is that this standard model does not really describe every single property of the universe. So we think that it might be somewhere some hint of new particles. So the standard model might be actually a part of a much larger model that we still need to describe. Now, let's go back to the big data part. So the Higgs boson was announced its discovery in 2012. So what you see here is basically integrated luminosity, means the amount of data that we have collected. So this means that in 2012, we discovered the Higgs boson with this amount of data. Compared to the amount of data that we are going to collect starting to 2026, you see that there will be a major upgrade in the Large Hadron Collider and in the experiment. So the question is, why do we need to collect this amount of data? Well, it's because all those particles outside the standard model are very hard to detect. They are very rare processes. So you see here, for example, for the discovery of the Higgs boson, that signal hides in the background. It's a very small signal. For example, there on the left, you see that tiny bump is a Higgs boson. Same goes on the right. We need a big amount of data, not only coming from the collision, but we also need simulated data because we want to compare signal with simulation. So simulation will be also a problem. So to summarize, at the LHC experiments, we have bunches of protons colliding every 25 nanoseconds. Particles produced in the collision leave traces that we want to study. Today, each bunch crossing, you have basically 50 simultaneous proton-proton interaction. This is called pileup. And starting from 2026, we will have the high luminosity LHC, and the number of simultaneous proton-proton collision will go up by a factor 4. So we have the two kinds of problems. One is the fact that the reconstruction algorithms, so connecting the dots, does not scale linearly with pileup. It has a combinatorial behavior. Then the fact that result of reconstruction has to be compared to simulation, and simulation is costly because you have to, for each single step that the particle flies through the detector, you have to simulate the interaction with the material. Then, furthermore, we are also upgrading our detectors with now this highly granular NCAP calorimeter, which is 600 tons. You have sensitive material, silicon, stainless steel as an absorber, and lead. So basically, what we will find out is that this detector is a 5D detector. 5D means that this is the dream of every particle physicist. So basically, you have that you can see the particle entering the calorimeter and showering and producing every single signal in each layer. And not only you have that, you have that each single 3D hit, it has also time and energy information. So it's really a 5D detector. And it's also not only the dream of every particle physicist, but it's also the dream of every machine learning developer, because, I mean, these are images, 5D images that you can apply machine learning to. Now, where are the opportunities for neural networks in reconstruction and simulation in high energy physics? So one is reducing the combinatorics by early rejecting wrong paths. I mean, if you know that a particle is not likely to go in a direction or leave two traces which are not compatible, you don't want to explore that path later. So it will reduce the combinatorics. You want to suppress the pileup, so the additional collisions that you get on top of the signal by applying denoising algorithms. For a simulation, you want to generate showers, the one that we just saw in the calorimeter. You want to generate shower really fast using probably GANs or whatever we will have by 2026. Identifying particles by looking at showers directly without going in the details of the heats. Regression of the energy. So you look at the shower and you say, oh, this is 50 gigaelectron volt pion. You want to classify jets, so narrow showers of particles produced by quarks or gluons. And last but not least, this is very important, you want to bring smartness earlier in the game. So some smart thing that today you could do offline, you want to do at the high level trigger or even at the level 1 trigger. So acting in the microseconds latency range. So the problem is that on big data, in the kind of data that we have, today we collect something like 100 petabytes per year, but we will get to the exabyte per year pretty soon. The development cycle is completely dominated by training. So this is why we started to develop a framework for distributed training. So what we support for training and optimization as well. So what we support are concepts, paradigms like downpour, in which you basically have that you distribute the same model uh, over workers, and the model communicates the updates through a centralized parameter server. So this is asynchronous in two aspects. One is the fact that the model replicas run independently, and then the fact that each worker runs on a shard of the parameters, so they also run independently on one another. The other one is the elastic average SGD. So basically, using a Lagrangian model, you basically apply, you basically have that the local workers are described as working under an elastic force, and basically you have that this elastic force links all the parameters, and you have a central variable stored by the master. So basically what you have is that the this central variable is basically a moving average, is a running average in space and time, and you can represent this as a tree-like structure with a Ubermaster and submasters. Then we also contributed to Horovod in order to add more MPI support to it. So basically the Horovod approach is basically an all-reduce approach. So you have that each worker has a small batch of data. It computes the gradient and the gradient of the loss. And then you have the all-reduce to compute the overall gradient. So since 1 month ago, now it's fully available for Keras and TensorFlow. We have a Dockerized version. However, some sites don't like Docker, so we are looking into Singularity for that for security reasons. Then we are also working on GEM. So basically, this is a variant of the distributed asynchronous SGD. So basically, this is you basically have a parallel between the asynchronous workers working together, matched to a dynamic of a target synchronous process. So basically, the fact that there is a target synchronous process is basically guarantee you the convergence, because the paradigm scales to to a very large number of asynchronous workers, and basically you have that the compliance to basically there is a matching between the kinetic energy of the proxy and the central variable, which is basically telling you the compliance conditions between the two, and say, okay, these parameters are good, please go on in this direction or not. And this can be done asynchronous. Going back to the optimization, starting from this very basic configuration for parallelizing Bayesian optimization, what you have is that what I have described, all the training concepts that I have described, can be basically plugged in a parameter set group. And then there is a master which basically distributes the new parameter set. So starting from this basic configuration, what you might have is that inside in each single parameter set group, you have multiple folds of your data. So this is in order to ensure stability of the results of the training. This is because if in the basic configuration what you have is basically that they will give you an estimate of how good the training performed with those parameters, but there will be no error bar. So by having multiple folds, you might get also that information. We also introduced here the all-reduced setup. So basically, here you might have multiple GPUs or multiple nodes with multiple GPUs in Horovod, and they will act as a worker in working together in a parameter set group with a single training master. Then one more work in progress. So basically all the previous approaches are also limited by the fact that the asking the computation of the next parameter set that you have might take some time. So you might want to offload the computation to some SK-opt workers, so the parameter set group are never idle. They can get a new parameter set to work on pretty soon. So this is to optimize basically load balancing. Then we are also looking in genetic optimization. You basically create an initial random population of chromosomes, and then you select for each, you let them evolve with some rules. So basically you have that at each generation, you clone the fittest 20% of the population, so the best parameters will be cloned. You might select or improve or apply mutations by choosing parents of offsprings and creating binary tournaments. You can also introduce sudden mutations. So basically, what you have is that at the end of the evolution, you will get the fittest chromosome in the final population, and this will be your final parameters. So on which resources we are running or trying to run. So some months ago, we applied for an allocation at CSCS. So basically the software is ready, but we are still waiting for it. We are creating a singularity image to run on Summit, but we are only running today on Titan. So some results will be shown, I think, in the next talk. So I would like to thank the Oak Ridge people for helping us. So going to the conclusion. So the high energy physics field is now entering all in this exciting new era of distributed neural networks. So what we have is that traditional algorithms together with neural networks might coexist in order to get the double crème out of our data. So what we are developing is infrastructure for large-scale production training and optimization. We are looking into implementing GEM, as I told you, and starting testing on different clusters as soon as we get some allocation for them. Thanks, that's it.
Thank you, Felice. There's already questions. So for this genetic evolutionary algorithm, so what are the parameters? Because in theory, you can technically let the whole network like self-assemble, right? Like Google is doing this with AutoML. So are you also putting this in, or it's basically first just you have a fixed topology and then you optimize the parameters, or allow you to build the network from scratch?
It's the entire model, and then you can think of something that, I mean, you get the fittest of each evolutionary algorithm, and then you rerun with those parameters. I mean, you can imagine a tree-like structure also for that.
I mean, but do you start with a given model, or start with a single layer, and then you assemble the model by doing that?
I think it's the entire model. Yeah.
Have you looked at this like population-based training stuff, which we just like, where you actually like you build a learning schedule for the whole thing, so you don't have like fixed hyperparameters that you can rerun with, but you change them during the course of the training as you go past the epochs. So then you don't have something you can repeat, but well, you can repeat it with the learning schedule, but you can't just repeat it with some fixed hyperparameters. So I think this is another sort of Google approach.
We haven't looked into,
but it might need different machinery if you're. So you're presumably building this genetic algorithm stuff yourself, right? You're not using some existing tool to do it. Right. but your actual, I mean, the software you're using is your own sort of software. Okay. Because yeah, it might be worth considering this, I guess, in building up this population-based training kind of approach with this.
Big picture question. So how much data do you think you need to successfully train the network? And where's the data going to be? And then where's the compute going to be that can, and how much computer are you going to need to compute that much data?
So
where's this going to be? Or maybe put them in the same place.
so all these applications that all these applications that that I described very quickly have completely different requirements. So, for example, so today we already simulate. We run a full simulation, which means that starting from interactions, we describe almost. It takes a lot of time to describe the interaction of particles with the detector. So by doing that, so we produce billions of events. By doing that, we could also train in the very same moment generative adversarial networks for generating showers in the calorimeter. So that is something that could happen in place. On the other side, for example, reducing later combinatorics by early rejecting wrong paths. I mean, training this can happen somehow in place, but the kind of data formats that we have does not really allow it. So it's better to extract those information from a full simulation and then inject back in a NumPy data format, which is then much easier. So the amount of data that we need for the first one, it's not much. It's terabytes. It's not much. For the pileup suppression with the noise, it's quite larger. Generating showers, I think we are going to the petabytes. This is for the amount of data. Then for the computation, today we are not much using on purpose heterogeneous resources because I mean we are not really profiting from them. So, but things are changing now. So the idea is to get more and more involved with high performance computing centers, where we will run basically all the training for this, and probably start running also simulation and reconstruction there. I assume that by 2026, the entire computing infrastructure will completely change.
Maybe to add to this, another aspect would be to have a HPC doing training as a service where we abstract the whole machinery to a physicist and then just give the data and the model, and then this could run anywhere essentially. Is there any other question? All right. Yeah.
When you say HPC doing training as a service, do you mean that for like domain independent, like the HPC center, like you would give for, or are you thinking something more?
That is a good question. Nothing. If you go if you training as a service, it doesn't have any HEP related or any HEP specifics. Maybe the pipeline of the data could be HEP specific, but the training itself is certainly going beyond the HEP. Right? If there are no other questions, let's thank you again.